Hi, I'm Scott Vaughn, and this is the rocket equation, and a two-stage rocket launching a satellite into orbit in Kerbal Space Program. As you may know, the physics behind a rocket's motion is expressed by Newton's third law of motion. As the rocket burns fuel and expels exhaust, it creates a force in the direction of that exhaust, and also an equal and opposite force in the direction in which the rocket travels. It's the same principle that explains the recoil of a gun when a bullet is fired. And the mathematics that relates this law of physics to the speed of the rocket is described by the rocket equation. The rocket equation, here in a form called the ideal rocket equation, or Tsiolkovsky's equation, indicates the change in velocity, or the delta V, that results from expelling a given amount of mass as exhaust at a given exhaust velocity from the rocket. You can see in the equation how terms for the initial mass and the final mass after the fuel is burned and the exhaust exit velocity all relate to the resulting change in the rocket's velocity. However, in this form of the rocket equation, it doesn't include terms for multiple stages or a payload mass that is distinct from the rocket, but we'll include that in a moment. In this video, our main goal will be to explore the math behind finding the theoretical optimal mass for each stage of a multi-stage rocket that is meant to reach a given target velocity. We begin with the ideal rocket equation shown here, but rewrite that equation to include multiple stages and a separate payload, and then use this to derive formulas for determining the theoretical optimal mass for each stage. We'll derive the formulas initially for a two-stage rocket, and then look at the results for rockets with 3 stages, and we'll compare our results with actual values of real rockets like the Saturn V, the Falcon 9, the SpaceX Starship, and with a model like this one built in Kerbal Space Program. Okay, so this video did turn out to be pretty extensive in length, so I will just identify here some of the major sections that I go through. First, an introduction to the method of Lagrange multipliers and overall what my goal is in the video. Then I get into some sort of algebraic trickery, a change of variables that makes it possible to actually do the method of Lagrange multipliers on the particular topic that I'm going to focus on. And in doing that, we derive formulas that we can then go through and calculate optimal mass for multi-stage rockets. And finally, it's a summary, some example calculations, for example, with the Saturn V, the SpaceX Starship, Falcon 9, and an example in Kerbal Space Program, and I'm going to talk there a little bit about other things that you could do to extend the work that I've done here. So this video is a lesson in the application of a multivariable calculus technique known as the method of Lagrange multipliers. And there's a good bit of algebra and pre-calculus involved here, so fasten seatbelts, as we're going to quickly accelerate through several stages of mathematics to reach this goal. I'm making this video for students in calculus, particularly those in multivariable calculus, or Calc 3. But if you don't know these topics, I hope I can still get across the overall general idea in such a way that you can still follow along, at least understand the conclusions, even if not every detail along the way. And to learn more about optimal rocket staging and Lagrange multipliers and a lot of other space science topics illustrated with both real-life examples and examples in Kerbal Space Program, and to learn more than just what I cover even on this particular topic in this video, check out my workbook at sites.google.com/KSP Math, where I have a detailed written explanation on optimal staging with Lagrange multipliers and how it is extended beyond just what I do in this video. I've also included practice problems and solutions in that online workbook. And the workbook starts at a level that is beginning algebra and progresses to multivariable calculus and differential equations, and covers many other math topics in space science that I think are all absolutely fascinating. So if you find this topic at all interesting, please check out that website for some other similar topics. The idea for this video originally comes from a project in the Stewart Early Transcendental Calculus book. The project in the Stewart book is at the end of the chapter on Lagrange multipliers, and it included simplifying assumptions that initially had me wondering how realistic it was. But then I discovered a very similar approach in another book, Orbital Mechanics for Engineering Students by Howard Curtis. And that book by Curtis is entirely devoted to the math, physics, and engineering of rocket science at an advanced undergraduate, even graduate level. And Curtis begins with the same approach as Stewart, and then extends those same results beyond what was done in the Stewart book. And interestingly enough, this topic is the very last section of the very last chapter in the Curtis book. Also, I'll mention that some of the very same concepts and methods I use here in this video, and as they are found in the Stewart and Curtis books, are also found in a workbook for high school students originally published by NASA in the 1980s called Space Mathematics, Math Problems Based on Space Science by Bernice Castor. So even though I'm not a professional rocket scientist and definitely can't speak to all the complex real-life engineering challenges involved in designing rockets, I do know the math used in each of these books, and I simply enjoy learning and sharing what I learn of these real-life applications in space science. And even better when we can have some fun modeling and testing that math that we're learning in a simulation like Kerbal Space Program. So in this video, we will consider some intro-level theoretical mathematical modeling of multi-stage rockets to determine the optimal mass for each stage of a multi-stage rocket, and we'll compare those theoretical results with the real-life Saturn V, SpaceX Falcon 9, and Starship, and with a model built in Kerbal Space Program. Okay, so to really get underway then, once again, here's the ideal rocket equation. In the ideal rocket equation, we have the initial mass m0 there. That's the total mass of the rocket initially at the launch pad or before any fuel is burned. This is the final mass, this is the exit velocity, and this is the total change in velocity. Of course, that's the natural log function. So here is a version of that rocket equation that allows for two stages and allows for a payload, and each stage has a different mass. So what we're looking at here is m1, like the stage 1 mass. And I'll sometimes also want to refer to it as a step mass because it's the mass for just stage 1. M1 is the stage 1 mass, total initial mass. M2 is the stage 2 initial mass. A will represent the payload mass. This is a constant, fixed parameter that's given at the beginning. And this S, this is a structural factor. So what that represents is some value between 0 and 1. And it represents the percentage of the rocket that is just a structure, like engines and tanks and the hull and all of the mechanical components other than the fuel. So the structural factor might be like 0.1, and if it's 0.1, that would represent that the structure of the rocket itself is 10% of the total filled rocket. So when it's fully fueled, it's heavier, and the structure is just 10% of the total mass. So if the S was 0.1, then 10% is structure and 90% is the fuel. And we have one other variable on there, and this is the exhaust velocity. And here, in this first part of the derivation, we'll assume that in each stage you have the same exhaust velocity. We can change that later, but for the first time through this work, we're going to assume the same structural factor in each stage, and we'll assume the same relative exhaust velocity in each stage. And then you can adjust that if you wanted to later. And so maybe another thing that's really important to sort of focus on at the very beginning here is this ratio, this mass ratio in this fraction in the argument of the natural log function. Notice that we had the initial mass and then the final mass. This is the mass after the fuel is burned. So if you think about each of the arguments here in each of these terms, this is the initial total mass of the rocket with the initial stage 1 mass, initial stage 2 mass, and payload. And what do we have in the denominator? Well, we have the structural factor times the stage 1 mass. So if, for example, it was, let's say, 0.1, then you would have 10% of that initial stage 1 mass remaining after the fuel was burned. And you would still have all of stage 2 and all of the payload as still the mass of the rocket, because it's only stage 1 that's burning its fuel in, that first stage of the during the first stage burn. This is the delta V that we would get. So I might want to write, so delta V1 is this entire term, and this is a delta V2, this entire term. This is the initial mass, and this is the final mass after the stage 1 burn. And in the stage 2 burn, this is the initial mass because we would have dropped stage 1. And so this is the initial mass after stage 1 is dropped. You have only stage 2 and the payload. That's your initial mass for stage 2. And then when stage 2 completes its burn, you have the final mass, which is some structural factor multiplied by that stage 2 mass. So again, it could be 10% of what the initial stage 2 step mass was. And then you still have the payload. Now, an interesting question that can come up here is that when you drop a stage, does that provide any additional velocity? Because you're expelling, aren't you? Aren't you expelling the lower stage? But no, we're not expelling. We're just imagining you just drop the stage. And so that lower stage that's being released would have the same velocity as the upper stage before it begins its burn. So there is no delta V that's gained by just dropping a stage. Now, of course, what we all witness is that as you're launching a rocket through the atmosphere, the lower stage drops away very quickly, but that's because it no longer has any propulsion and it has the atmosphere slowing it down. So they separate quickly, but if it were just in the free space without an atmosphere, actually the two stages would continue at the same velocity until the upper stage started its burn. So no delta V coming from releasing the stage. The only delta V that occurs is from each stage doing its burn, and that's captured in this case by two burns on two different stages. In this derivation, we will assume the structural factor for each stage is the same, that is, S is constant, and we'll also assume each stage expels exhaust with the same velocity. That exhaust velocity, again, is that value C, and we'll assume that that's constant and the same in each stage. And we could change these assumptions later for different structural factors in each stage and different exhaust velocities at each stage. And I do go into that in the written explanation and the practice problems in the online Kerbal Math and Physics lab on my website. But perhaps for a video introduction here, it's easiest if we just start now with this assumption of similar stages, the assumption that each stage has the same structural factor and same exhaust velocity, and do the derivation that way. So in this video, we're going to assume S is constant. For example, S could be 0.1, and the C is constant. For example, C could be 3 kilometers per second as the exhaust velocity. And also, you can assume that A is some fixed constant value representing the mass of the payload. And of course, there's the delta V, the total delta V, that's going to be some given value that we're going to target as a objective to reach a certain velocity. For example, 10 kilometers per second might be your final velocity that you want to achieve as orbital speed. And looking ahead just for a second here, this is the setup that I was just describing for a two-stage rocket, but if you wanted to imagine what that would look like extended to three stages, just to see the kind of general idea that I'm following here, this is the setup for a three-stage rocket, right? This is the initial mass of the three-stage rocket. The step masses, mass 1, 2, and 3 for each of the individual stages, and the payload, and that all represents the initial mass. When stage 1 burns, it will be reduced to some fraction of its original initial mass. Let's say perhaps the S is, let's say, 0.2. So if it was 0.2, then you have 20% of that initial mass remaining after the burn. And so all of these terms summed together represent the final mass after the first stage does its burn. And then this altogether would be the delta V achieved by just the first stage. Once the first stage is then released, you no longer have all of that structural mass, and you can then initiate another burn on stage 2. This would be the initial mass for this of the entire rocket, with stage 2, stage 3, and the payloads all there. As stage 2 burns, when it's completed, the denominator here represents the mass of the rocket after stage 2 burns. So you'll have some fraction of the step mass of stage 2 remaining, but you still have stage 3 and still have the payload as the mass of the entire rocket. So then finally, in the third stage, total mass as the third stage initiates its burn, its total mass is stage 3 and the payload. And then after stage 3 burns, then you'll have some fraction of the initial mass remaining and the payload remaining. And then, of course, you could drop stage 3, but there'll be no additional delta V gained by the payload at that point. Of course, the payload could have its own propellant and often does, but that's not included in this. We're just looking at what total delta V is gained by the three stages launching a rocket with a particular payload. So we basically now have all the parts that we need to approach the concept of the Lagrange multipliers. And when you do Lagrange multipliers, you need to have an objective function and you need to have a constraint function. So the objective function is whatever it is you're trying to find a maximum or minimum value for, and the constraint is just some equation that has to be true simultaneously when you find a minimum or maximum or whatever it is you're trying to optimize. So in this particular context, in this problem, what we're trying to do is minimize the total mass while we have a constraint that is the velocity that's required for orbit. So you could say that in this case that we back up now to the two-stage rocket example, you've got two masses that are variable at this point. We're trying to figure out what the mass, step 1 mass and step 2, stage 2 mass individually, what they should be optimally to have basically the lowest total mass. And that's what we're going to try to do, minimize this objective function that is, you could call M0, the initial mass of the entire rocket in the case of two stages, stage 1, stage 2, and payload. We're trying to minimize this at the same time. We're trying to achieve some particular velocity. So VF, the final velocity that's required for for a particular objective like reaching orbit. Or escape velocity, something like that. So this is a separate function, the way that I have it written here, that will ultimately become an equation that we have to recognize in the method of Lagrange multipliers. It's an equation because we put a constant value in there for the velocity that we want, and so we take that equation as a constraint and try to minimize the total mass. So these are the two functions. Each each function is a function of two variables in this case, and of course it could extend to 3 variables or more, depending on the number of stages. But the functions that you see identified here and here, if we go directly into the method of Lagrange multiplier, with these two functions written as they are here, the algebra gets pretty unwieldy and the calculus gets pretty intense to do by hand. And so in order to get an analytic solution, because with the setup with the similar stages, we can get an exact analytic solution. We don't have to use the computer to find the solution for us. We can of course we'll use the computer and the calculator to get very accurate values, but we can come up with a theoretical exact value with the assumption of similar stages. So another reason to do that first. But in order to do that, basically through the algebra and calculus, what we'll do is we'll make a substitution with some new variables that make the process of doing this algebra and calculus much more, much easier. So the functions f and g given here in equations 4 and 5 will be difficult to manipulate precisely in both the algebra and calculus of the method of Lagrange multipliers. Therefore, to simplify the anticipated steps that we will follow, we define these new variables in terms of the given variables being c and s and a, and actually m1 and m2 we'll rewrite. So there we go. So what we'll do is we will define n1 to be this mass ratio in stage 1, and we'll define this variable n2 to be this mass ratio in the stage 2 burn. And with those substitutions, we'll rewrite the functions f and g into a new form where it'll be a little easier to actually do the method of Lagrange multipliers analytically and see the solution play out in a process of steps that we can actually write out by hand, derive a formula. Then, of course, we can put that formula into Excel and get or a calculator and get quick answers for changes in our variables. So in order to rewrite those two functions, the objective function and the constraint function, we'll actually need to do some algebra manipulation here. So we need to show that this actually, this equality is true, and we need to show that equality is true, and you'll see why that is in a moment. So let's just run through that first. Okay, so absolutely understandable if this is a little confusing, what the heck is going on? At the moment, I've just replaced n2 in this expression here with n2 as I had defined it, and followed through some algebra to arrive at that conclusion, that this expression is equal to that expression. And these are all little tiny steps I will try to put together in a moment when I've completed them, but we've got to do some algebra here to collect all of these parts that I can then put together. So if it's not entirely clear what's going on, hold on a second. The next thing that I wanted to accomplish as a little step along the way here is just show that regardless of the number of stages, the minimum value of m0, being the total rocket mass, occurs at the same point as the minimum value of this expression, where a is a constant and m0 is greater than 0. And actually I need to include that a is bigger than 0 as well. It's positive. So the reason that that's true ultimately is just because the natural log is a strictly increasing function, and the minimum value of the input corresponds to the minimum value of the function. I made that a little bit more formal in the argument that I justify the conclusion by here, just saying that if you took a derivative with respect to m0, the independent variable here, the derivative of the natural log, of course, is 1 over the argument. There's a chain rule factor here, 1 over a. I'm taking a to be a constant. And if you take this 1 over m naught over a and you flip, and then of course the a's would cancel. And so this is the derivative of that natural log of m0 over a, and that's a positive. So just saying that the function is strictly increasing, a quick picture of the natural log of x, that's the natural log of x, and the minimum value of that function corresponds to a minimum value of x. So a minimum value of m0 corresponds to a minimum value of m0 over some constant, which corresponds to a minimum of that function, which is the next little piece of a series of arguments, algebraic arguments that I need to put together to make a conclusion. So I'm getting there. I got one more important one here, which is just that expression that I was just looking at, that m0 over a. You might think, well, why did you even think to consider that? Just now recognize that I could write that m naught over a as this expression in terms of these new variables, which of course looks much more complicated, but it has a value in a moment when we tie in the ln of that expression. So anyway, the point is that if you take m naught over a, I have just showed that this expression is equal to that, and this expression is equal to that. So this is the m naught over a in terms of these new variables n1 and n2 and just some constant s. And m naught over a, of course, you could say is this expression times this expression, because notice that these guys would cancel out and we have this numerator divided by a. Perfect. So this can be expressed in terms of n1, and this can be expressed in terms of n2, and that means when you multiply those two together, you got two factors of this 1 minus s, so 1 minus s squared. The n1 and the n2 can be multiplied together, and these guys you just have to multiply together in the denominator. Now that looks much more complicated than this guy, but when you do an ln of this guy and therefore an ln of this guy, that we can simplify with the ln, and the whole thing is written in terms of the new variable in a way that taking the derivative is easy, and all of the following steps of the Lagrange multiplier are easier in that situation with those new variables. So this is the last thing that I want to put together, and then we can proceed with the Lagrange multiplier. I want to show that the ln of m naught over a is equal to all of these terms, which are written with the new variable n1 and n2 and just some constant s. So we've just established that m naught over a is equal to this expression, right? We just showed m naught over a is equal to that. So I'm just replacing m naught over a with all of that, and then its properties of the natural log that produce the result that we want there at the top of the screen. And that's the right-hand side that I have there, so that's part's done as well. And that was it. That was the algebra that needed to be done. Now that we have this established, we've got a new function, f and g, that we can apply Lagrange multipliers with, and that will actually play out much easier with these new variables n1 and n2. So recasting the question now, we have an objective function, which is this fn, that is this expression that we just derived. It actually still relates to the initial mass, but it's written in terms of these new variables, and it looks pretty cryptic and bizarre at the moment, but we can actually do Lagrange multipliers easily with this compared to where we were with the original variables. And this is our constraint. Remember, the n1 and the n2 are those mass ratios as we had defined them just a moment ago, and this will end up being some equation because we'll have a fixed velocity that we want to achieve, and with that constraint we're going to try to minimize this function. So that's where Lagrange multipliers comes in. All right, and then when you approach doing Lagrange multipliers, one way to sort of capture the whole thing in a sort of mechanical process that you just follow step by step is to generate a new function that combines your objective and constraint all together. That's what h is. It's a function of the variables of the question that you're trying to optimize, which is now my n1 and n2. You introduce the Lagrange multiplier, which is this lambda, as a new variable. You see, there's my objective function all the way, all of this. That's the f sub n. The objective function in terms of n1 and n2, then you say plus lambda times the constraint. But in order to do it this way with this function h, what you have to do is take your constraint equation and rewrite it as a function equal to 0, or rewrite the equation equal to 0 and rewrite that equation equal to 0 and take that as a function that you then use here. So notice how the c ln n1 became a negative, c ln n2 became a negative. I'm moving them to the other side of this velocity final and creating this function that I want to set equal to 0. That's what this is here. Now, this is a kind of like mechanical step-by-step process of completing the Lagrange multiplier method, but I can take a few minutes right here to sort of explain visually what's going on, and then I'll go through the rest of these steps and then come back and just try to connect that visual understanding maybe one more time. So here's that objective function in terms of these variables n1 and n2 written out here on the right hand side, and I've typed it into GeoGebra. I'm just using x for my n1, I'm using y for the n2 variable in GeoGebra here, and s is just a parameter that I have a slider for. It's a constant that we'll look at this function, a graph of this function in a moment. And then I also have the constraint, this function g, in the expression over here on the right hand side, where it's equal to some final velocity. I have that expressed right here in terms of those same variables n1 and n2 that I've called x and y, just equal to some constant. So to just sort of visualize what's happening at this moment, this surface here is the function of two variables, x and y, or n1 and n2 in our application. And you know, the x, these are increasing values of x and increasing values of y, and actually it's symmetric. It's symmetric about that line y equal x. The effect of that slider is basically just to change that surface. But the principle of Lagrange multipliers is that we're looking for a minimum value of this function, but subject to the constraint that is down here as this curve. So changing that value c adjust where that curve is. And basically what you're trying to do is, if you stay on this curve, which satisfies the constraint that the velocity has to be 10 kilometers per second, for example, what's the minimum value of this surface for points along that curve? And so it's going to be some point, some xy value, or some n1, n2 value that we can translate back into m1 and m2 in the actual application. And again, here's that function that I'm trying to find a minimum value for. It's actually something you can visualize as a surface, because there's the n1 value, let's say x, and the n2 value you can imagine as a y value, a function of two variables. you're trying to find a minimum for this function, that actually was the minimum of this ln of m naught over 0, but that really corresponds to the minimum of m naught as well, right? And so you're finding a minimum of this function subject to this particular constraint. And another way of looking at the concept of Lagrange multipliers is something that's visualized over here in this graph. Basically what we're doing is we've got level curves graphed for this particular function. So the 2 log 1 minus s, here log is actually the natural log in Wolfram Cloud. So this is the natural logarithm function. 1 minus some parameter s, just like I have here, where I've set it to be 0.1, for example. I set the c value to be 3. And that's showing up right here in the constraint. But once again, looking through my objective function, I have 2 times log 1 minus s, the log of x, or n1, and the log of y, or n2. And again, it's the natural log. And then natural log of 1 minus s times the n1, and minus the natural log of 1 minus s times the n2 value. And I've just plotted it in a window 0 to 10, 0 to 10. So just positive x and y, or n1 and n2 values. And I just went through and had it plot some contour lines, which are these lines. Actually, there we go. See that 5 right there? Those are all the points where the function hits 5. And these are all the points where the function hits 6 and 7, which is what I'm asking it to plot. And there's the last one, 8. And these are values where the function is bigger than 8. You could see that in this picture right here, where the function is increasing as we go to bigger and bigger x and y values, or n1 and n2 values. So that's a plot of the contour, the level curves of the function f, and superimposed on top of it is the constraint in a particular example with the c value being 3 and the final velocity being 10. Let's go back and look at that here. Here I have c equal to 3 and the final velocity equal to 10. So that's showing up as that blue curve right there. That's the constraint. So we're trying to find a point along that curve where you have a minimum for this, where s is, let's say, 0.1. So what is that value? Maybe it's around 5 something. It's kind of hard to visualize here, but this is 4 and 6, so perhaps around a value of 5 for both the x and the y, or n1 and n2, where you have a minimum value and you're on that constraint curve. It's definitely easier to see here the point where these two, the level curve and the constraint, are tangent. And that's where the real key for understanding really what Lagrange multipliers are doing is finding a point. It's finding the point where the gradient of the objective function is parallel to a gradient of the constraint. That happens when the two curves are tangent to each other. Their gradients, because the gradients are perpendicular to these level curves, the gradients are going to be parallel, not necessarily in the same direction, they could be in exactly opposite direction, but it'll happen at a point just about, well, right around here, which happens to be where the function, in this case f, is hitting a value of about 4.62. That's why I included that one in particular, because I was looking ahead to sort of see what was going to happen. But it's a value of roughly 5 something for both the x and y value, which means 5 for the n1 and n2 value. And we'll see that in a moment come up when we actually do it analytically. But yeah, that's actually the visualization of what this now is going to try to locate, that point where those two curves are tangent. The level curves and the constraint curve are tangent. That's what this does, this process now, the calculus. Okay, so we're now ready to apply the method of Lagrange multipliers. We have an objective function here, we have a constraint function here, and we've put it all together in this function h. And this begins the process of solving by Lagrange multipliers. And if you're feeling a little bit lost at this point, I'm going to go back and sum it all up once I'm done here. But basically, we've got this 1, 2, 3, 4 steps to solve for the formulas for the mass of each stage of the rocket, and then we can start looking at examples. So this is the next thing to do. We'll take that function h that's written there and find partial derivatives. Doing those partial derivatives will look like this. The first one, the partial of h with respect to the variable n1, going through and taking a derivative with respect to n1. So this doesn't have n1 at all, so it will go to 0. The derivative of this guy is 1 over n1. And then we get to this term, and there's no n1, so that goes to 0. This has a factor of n1, so the derivative, what happens here, is you get minus 1 over the argument, 1 minus s n1. But then you get a derivative by the chain rule, you get a derivative of the inside, which is a negative s. So we could say minus s here like that. And that takes care of this term, and then we look at that term, and of course it's going to go to 0 because it's no n1. And when we take a derivative of this with respect to n1, what we end up getting is just the the lambda minus c times 1 over n. So that's the derivative with respect to n1, and it's going to work the same way doing a derivative with respect to n2. So that's actually now going back and looking at this, it goes to 0. You look at this guy, and it goes to 0. There's no n2. This will give me 1 over n2. Through here, this term goes to 0, and you end up with just the lambda minus c over n2. And that's the derivative with respect to n2. And then finally, the last thing to do here is a derivative with respect to lambda. Taking a derivative with respect to lambda of this entire function, this goes to 0, 0, 0, 0, this goes to 0. All of these are 0 because there's no lambda. And actually, with respect to lambda, all this is a constant. So you end up with just that expression, taking a derivative with respect to lambda. The only variable when you take a derivative with respect to lambda is lambda, so this is all just a constant in that derivative. So that produces velocity final minus c ln n1 minus c ln n2, and that's the result for the derivative with respect to lambda. The next thing that we're doing here, now that we have completed that step, the next thing that we want to do is just solve this system. And what the significance here is basically that we just take all those derivatives that we just did and set them all equal to 0, and that's the standard procedure that you follow in this method of Lagrange multipliers. It's essentially, it's looking for the point where the gradient of the objective function is parallel to the gradient of the constraint function, but we just did it in a sort of mechanical way that created this as an initial step in the process. But that system of equations is basically the gradients parallel and the constraint satisfied. So it's just a matter of taking all of the partials and setting them equal to 0. So that's our kind of question number 2 here, is just solving, setting each of these equal to 0. That produces that system of equations. We would just move this term over, and you could move each of those terms over, and you're back to this. So that is just the next step after setting every partial equal to 0. You would do that anytime you're following this process for the method of Lagrange multipliers, is you take all the partials and set them equal to 0. So what I want to do now is solve this system, and the way you can do that, actually, what I'm going to do is I'm going to multiply by n1 on both sides. Here, I'll multiply by n2 on both sides. So if I have an equation 1 and an equation 2, that equation 1, you get 1 plus Sn1 over 1 minus Sn1 equals lambda c. And then in that equation 2, multiplying both sides by n2, I'm going to get 1 plus Sn2 over 1 minus n2 equals lambda c. And that means this expression equals that expression because they're both equal to lambda c, so we set them equal. 1 plus Sn1 over 1 minus Sn1 would have to equal 1 plus Sn2 over 1 minus Sn2. And then, of course, the 1's you can cancel from both sides. Sn1 over 1 minus Sn1 would equal Sn2 over 1 minus Sn2. Let's multiply, well, actually, how about we cross multiply? So Sn1, 1 minus Sn2 would equal Sn2, 1 minus Sn1. So Sn1 minus S squared N1 N2 equals Sn2 minus S squared N1 N2. So we'll cancel these terms from both sides. So Sn1 is Sn2. So N1 would have to equal N2 if all of these equations in this system are true. If all of these are simultaneously true, which they must for the solution to the system of equations for the minimum of the objective function by the method of Lagrange multipliers, we need the solution of this system. And in the solution of that system, we've been led to the conclusion that the N1 and N2 values have to be the same. If you remember, what were they? They're the mass ratios in each stage burn. So the mass ratios are the same, even though the individual masses don't have to be the same. We'll see that in a moment. But once we have N1 and N2 equal, then you can go back to the third equation in that system and say, let's just say N1 is and N2 are just equal to some common value that we just call N, and now we can solve for that, right? So if I'm using this third equation here, the third equation in that system was the ln of n1 plus c ln n2 has to equal velocity final, but we've just discovered that n1 is equal to n2, and we'll call that n. So we could say that final velocity is c ln n plus c ln n, and that means that we've got velocity final has to equal 2 times c ln of that mass ratio n. So we can solve for that mass ratio n that is equal to both of the mass ratios. So we have velocity final over 2c is ln of that mass ratio n. So e to the final velocity over 2 times the relative exhaust velocity is n. So that's a pretty useful result as we're going forward. This is n, which is n1, which is n2. Actually, I see now that I've just done that part. Solve for n in terms of the final velocity and the exhaust velocity. The answer there is n is the number e to a power of whatever that final velocity that we need for our target speed divided by 2 times the exhaust velocity if you have a two-stage rocket with the same exhaust velocity each stage, and this also assumed the same structural factor in each stage. So under that assumption, then we're able to get this, we're headed toward an exact solution, because now that we have n, which is both n1 and n2, we can go back and solve for the original values m1 and m2. So how do you do that? We're really close, because basically once I have that, then I'll start looking at some examples. We need to scroll way back to a very early stage in this process where we had actually defined these values n1 and n2 in terms of our original mass step masses. So we're going to use these to now solve for the m1 and m2 in terms of n1 and n2. So the way to do this is kind of backwards. You solve for m2 first, and then once you have m2 in terms of n2, then you can solve for m1 in terms of m2 and N2, right? So solving for M2. That's it. That's the stage 2 mass, individual mass, in terms of the N2 value, which is actually the N value, and actually the N1 value. The way I'm actually going to write it when I put it into Excel is I'm going to flip it around and say N2 minus 1 over 1 minus, let's say, SN2, and then just multiplied by A. So in other words, what's happening is once you establish what the payload is, the stage 2 mass is some multiple of the payload mass based on what your target velocity is and what your exit velocity is, and you calculate that with that n value with this formula. And then if it was 3 stages, it's going to be similar, and then we're almost there. So we can now figure out what the M1 mass would be. I'm going to start with that. I'm going to solve for M1, knowing M2 now, and N. This pretty much follows the same kind of process that we just saw play out for the M2. It's the same process. So by the way, I could be writing N instead of N1, because I know N1 and N2 are the same and they're equal to something I called N, but I was just copying what I saw there already on the screen and writing N1, but I know that that's actually something I could just call N. So if you would prefer doing that, that works just as well. That's good. That's it. I'm going to just change the way it's written when I put it into Excel. I'm going to say M1 is, what I'll do is I'll just flip this around and say N1 minus 1 over 1 minus Sn1. And of course I could call those N. And I'll just say it's multiplied by M2 plus A. In other words, if I want the stage 1 step mass, I'll just multiply that same factor I had before times the mass of stage 2 and the payload. So M1 is, let's just call it N, because we know N1 and N2 are the same, 1 minus Sn, and then it's just the combined mass of stage 2 and A. So this becomes a kind of like recursive process where you keep getting the lower stage once you know the higher stage. So let's look back again and compare with M2. M2 is right there. And I could have just written it as N rather than N2. So we could write it like that. So conclusion, we've got this factor N minus 1 over 1 minus Sn that we multiply by the payload mass to get M2, and to get M1, mass of the first stage, you take that same factor, N minus 1 over 1 minus Sn, and you multiply by the stage 2 step mass plus the payload. Oh, actually, that's not quite answering the question, is it? It says in terms of final velocity, exit exhaust velocity, and structural factor S, and those figured into the value of N. So it's just recall that N was this e to a power final velocity over 2 times exhaust velocity, and so we could just replace it here. That's the stage 2 step mass analytic solution, exact solution. Similarly, that's the exact analytic solution for the stage 1 mass for the 2-stage rocket with a given payload, structural factor, and constant relative exhaust velocity. Those are formulas that we can now plug into Excel and change the numbers and look at results and compare it with real-life examples. Okay, so here's a summary of what we have achieved so far, and realizing that the summary takes a full page itself, it's probably a good idea to stop for a quick summary. Here, what we've concluded is that given some payload mass A, some rocket exhaust velocity C, structural factor S, and some target final required velocity Vf, we can compute the optimal mass of each stage for a two-stage rocket using these formulas. We need to get this value n that involves the target velocity and 2 times the exhaust velocity that is the same velocity for each stage. Once you've got that n value, that figures into this factor here that we can use to multiply by the payload mass to calculate the mass of stage 2, and then to calculate the mass of stage 1, you use that same factor, n minus 1 over s times n, and just multiply it times the mass of stage 2 and the payload together, summed together like that. And then really, ultimately, the entire initial mass of the rocket, theoretically optimal total mass, is the sum of stage 1, stage 2, and the payload. And that's the conclusion that we reach. So that's really easy to put into Excel and look at some examples and change the values for different examples. And so let's do that first with a very simple example that we can then also compare with those graphs that I was looking at earlier in GeoGebra and Wolfram Programming Lab. Okay, so here's the Excel file where I have inputted these formulas, and at the moment I'm just going to focus on this section here for the two-stage rocket. And you can see that I have input cells for the payload mass, that's A, the structural factor, that's S, the exit velocity for each stage, which is the C value, and the final velocity required, which is this Vf. Now, one thing that you might be wondering is about the units, and actually the units really don't matter. You can use whatever units you want. Here I'm just calling it metric tons, but it could have just as well been kilograms, of course. A metric ton is 1,000 kilograms, but also interestingly, you could just say pounds. Now, of course, pounds isn't really a measure of mass. It's a measure of force at the surface of the Earth. So, but it would still work because the output that you get is in the same units as the input with respect to this measure of mass. And so you could really just talk about weight at the surface of the Earth if you wanted to put something like, let's say, 5,000 pounds here, or anything measured, in terms of the weight at the surface of the Earth, that would translate to the same units in the final answer. Similarly, with the exhaust velocity, you can measure that exhaust velocity in meters per second or feet per second or miles per hour, whatever unit of speed that you want to use for the exhaust velocity, as long as you're consistent with the unit for your final velocity for the actual rocket itself. As long as they're using the same units, it'll work out to be the same answer because that value of n, the units cancel in that point where you're calculating the n. So what I thought would also be kind of interesting here is what is that n? If you recall back earlier as I was looking at the general concept of Lagrange multipliers, and I had this picture on the screen, what this represented was this blue curve here being an example constraint. Here I have a constraint where it's basically 3 natural log of x plus 3 natural log of y equal to 10. So this is all the points in the xy plane where that equation is true. That represented the constraint, with the 2 exhaust velocities at each stage being 3 at the same for each stage, and a final velocity required of 10, let's say 10 kilometers per second. That means that you've got to pick a point along this blue curve. And what we were trying to do is figure out the point along that blue curve where we had a minimum for our objective function. And our objective function was this thing that involves the natural log of the n, and also figures, the s value figures into that function. And so it's this point right here where we're finding the minimum. It's about 5.3 is what that point is right there. And you can also see that here in a three-dimensional graph where I have the same constraint, let's put that at 3. So I have the same constraint g, that's this blue curve, but now you can see the function f as a function of the two variables n1 and n2 that ended up, we realized that at the minimum n1 and n2 are equal, and I just called it n. And that minimum of that surface is really at a point where both the x and y values are the same, and it looks like it's something around 5.3. It certainly looks that way in the graph as well, and I can see that that's precisely the value that I'm getting here when I take the function e to a power that is the final velocity 10 divided by the escape velocity, or the exhaust velocity 3, that's multiplied by 2 because of the two stages. So that's the 5.29 something there. Then actually you need to take that n value, put it into this factor n minus 1 divided by 1 minus Sn in order to then multiply that by the stage, the payload mass, which I used just 1 metric ton. So this would be the stage 2 would be roughly 9 metric tons, and stage 1 theoretically optimal value would be something around 92 metric tons, making a total mass of about 100 metric tons theoretically optimally with this target velocity and this exhaust velocity and this structural factor to lift 1 metric ton into low orbit, presumably low Earth orbit, since I'm using a value of 10 here, takes about 100 metric tons of mass to achieve that 1 metric ton payload into orbit. Another thing that's going to be happening as we go along looking at the examples is that this is not the orbital speed in low Earth orbit. Orbital speed is something around 7.8 kilometers per second. But what I have to do is increase the total required, because part of the process of reaching orbit is traveling vertically. And that is not contributing to orbital speed. You have to travel vertically in order to get out of the atmosphere. And not only going vertically, you're also going through the atmosphere, and that creates burns a lot of fuel just to fight that air resistance. So there is drag losses and gravity losses as at the initial part of the launch as it's trying to reach altitude to get into orbit. So that's why that's increased to 10 as a typical example. Okay, so now let's take a look at an example. This question number 5 here. The SpaceX Falcon 9 is a 2-stage rocket capable of launching about 23 tons to low Earth orbit. Part A, assume a constant structural factor of 0.04 for each stage, and a relative exhaust velocity of 3.5 kilometers per second, and a target orbital velocity of 10 kilometers per second. And by the way, really, about 7.8 kilometers per second is orbital velocity in low Earth orbit, but we include a little extra delta V in the budget here for what's required due to the velocity required to reach altitude and travel through the atmosphere. This is fuel lost going vertical to reach space, and due to air resistance, it doesn't contribute to the velocity parallel to the surface needed for orbit. So we'll find the theoretical optimal mass for each stage of the Falcon 9 and the total mass of the rocket, and then we'll compare that with some real values for the actual Falcon 9. So here in an Excel spreadsheet, I have for the 2-stage rocket input values for payload, structural factor, relative exhaust velocity, and required final orbital speed, or final delta V requirement. So these are all inputs. Here's the first calculation, this n value. This is the value that we already found out theoretically. It had to be e to a power of that final velocity divided by the number of stages, it turns out. In this case, 2 times the exhaust velocity, which is this value in B18. So what I'm computing here is the e to a power, this amount in cell B19 divided by 2 times the value in this cell. And so that gives me the n value. And then once I have the n, then I can do this calculation that I need for the mass of each of the stages that we've already derived, as you can see here. And now this is that previous cell there, B23, that value times the value in B16, which is the payload. So this is the factor n minus 1 over 1 minus Sn multiplied by the payload mass. So that's the stage 2 theoretical optimal mass, about 88 tons, let's say. And then here's the stage 1, about 421 metric tons. Combining stage 1, stage 2, and the payload, we're at about 532 metric tons total. So let's compare what the actual values are for the Falcon 9. So this is the SpaceX website, and here's a section for Falcon 9. With the Falcon 9, you get some basic data here on the website. Looks like total mass. This is 549,000 kilograms, which would be about 549 metric tons. And payload to low Earth orbit this is where I'm getting the 23 tons, roughly 23 tons. So we'll go to another good source, Wikipedia. This is rocket specifications, first stage, second stage, mass with propellant, 433 metric tons and about 112 metric tons. So I think the actual values are fairly close to these theoretical values that we've just calculated, particularly considering the number of assumptions, simplifying assumptions that were made. Okay, so what we've just computed here is with a payload of about 23 tons, theoretically 88 tons for stage 2, and theoretically 421 tons is optimal for stage 1, giving us a total of 532 tons. Meaning that the payload, representing about 23 tons out of the entire total mass, the payload is about 4%. And comparing with actual approximate values, of course, the payload isn't always 23 tons. In fact, I don't think it's ever actually reached that value. It's been just sort of just less than that. But if I use 23 tons for the payload, and we had an actual stage 2 mass about 112 tons, stage 1 about 433, making, if you add 23 with all of these, about 568. You can see that I've computed that the payload is about 4% of the total mass of the rocket in actual practice as well. Very, very close to the theoretical result, even with the assumptions that we've made here. And speaking of that, I thought we could just list again what those were. So it was the fact that we were assuming similar stages, that is the same structural factor on each stage and the same exhaust velocity on each stage. And we didn't really include how the first stage would actually have to do more of the work required in overcoming gravity and air resistance before the second stage could really accelerate up to orbital speed. So that is a practical consideration that would make for a more realistic answer. So let's move to this example. The Starship and Super Heavy booster, which together also makes a two-stage rocket that's currently under development at the SpaceX site in Boca Chica, Texas. It'll be a two-stage rocket with the first orbital test flight possible this year in 2022. Based on information provided at the SpaceX website and on Wikipedia, the Starship is intended to lift 100 metric tons or more to low Earth orbit, to the Moon, and to Mars. So let's assume a payload of 150 metric tons, a structural factor of 0.06 for both stages, the Starship itself and the Super Heavy booster. Let's take a relative exhaust velocity of 3.7 kilometers per second for each of those stages. And if, again, we want a total delta V of 10 kilometers per second, what is the theoretical optimal mass required for each stage? So back to the Excel file, let's put in 150. Let's put the structural factor at 0.06, but we'll increase the speed for the relative exhaust relative exhaust speed to be 3.7 kilometers per second, and keep that target at 10 kilometers per second, and we get about, let's call it 559 metric tons for stage 2, about 2,642 metric tons for stage 1, and altogether 3,351, let's say, metric tons, theoretically. Okay, and now trying to get some current estimates for the Starship and Super Heavy. This is the Wikipedia site, and I'll click on the description here. And right, for the Super Heavy booster, the value that I'm going to take here is that the booster's tanks can hold about 3,600 tons of propellant, and the dry mass is somewhere around 200 tons. So I'll put that together and make it 3,800 tons for stage 1, the Super Heavy booster. And for stage 2, the actual Starship, here it says dry mass maybe 100 tons or less, and main and 2 header tanks that provide 1,200 tons of capacity for propellant. So putting that together, let's say about 1,300 tons for the stage 2, the actual Starship, dry mass and propellant together, making 1,300 tons. Okay, so here are my theoretical optimal values compared with these estimated actual values that I can find looking these up on Wikipedia, and it wasn't quite as close as it was with the Falcon 9, and there's a lot of things that could play a role in the discrepancy here. I mean, there were a bunch of simplifying assumptions here that make this theoretical model difficult to fit to the actual real design. I mean, we had a number of assumptions such as, of course, the similar stages, the same structural factor on both stages, and the same relative exhaust velocity in both stages. And we're not including in the theoretical model how that stage 1 would do most of the work overcoming gravity and air resistance, and I'm not including anything for fuel reserves for landing. And also there are some assumptions here that could really change the outcome in the theoretical model when it comes to what is the actual orbit altitude required, what is the delta V required, the target delta V, depending on the orbit altitude and whether you have fuel for a transfer orbit. So all of these are complications in the real design of the rocket that are not included in this very simple theoretical model, and can certainly account for that discrepancy. Like here, theoretically, maybe the payload is 4.5% of the total mass of the rocket, whereas according to the data that I'm finding there on Wikipedia, maybe it's closer to 3% of the total mass of the rocket. Okay, so I'd really like to look at another example and compare with the Saturn V. That just seems like just gotta get that included. And I also said I'd look at an example with Kerbal. So to study the Saturn V, of course, that's a 3-stage rocket. So you could go back and redo the work that we had done for the 2-stage, extending it for the 3-stage, but the results are not surprising at all. It followed exactly the same pattern that we had just followed in 2 stages, and the results are, you can see them right here. You'd have to calculate this n value, which notice that it's just the number e raised to a power of the final velocity that you require divided by 3 times that relative exhaust velocity of each stage. All of this, of course, again, depending on the assumption that every stage provides the same relative exhaust velocity, which isn't really the case, but it's a simplifying assumption that allows us to get this single formula that is fairly accurate to what in practice actually happens. So it's a good starting point for a theoretical model, right? So that's our n value. And then to find the mass of stage 3, you just take that n value, use this factor here multiplied by the mass. So the mass, the payload mass, doesn't figure into this. It's just the total mass of the rocket just scales with the payload. So the larger the payload, the larger the stage 3 and all of the subsequent stages, and they follow along in a similar pattern as was derived already for 2 stages. So you just, for stage 2, you just take the 3rd stage, plus the payload, multiply that same factor that involves n and the structural factor, take that same factor now, n minus 1 over 1 minus n times s, and just multiply it by the mass of stage 2 and 3 that had already been computed. So you really have to do this sort of recursively, get those guys first, then you have this, and then you can calculate stage 1 mass. And so now we can take a look at an example here with the Saturn V. So the Saturn V launched the Apollo missions to the moon between 1969 and 1972, and it was a 3-stage rocket that carried a payload of approximately 50 metric tons to the moon. The payload consisted of the command, service, and lunar excursion modules, and it provided the astronauts the capability to land on the moon and return to Earth. So let's assume a structural factor of about 0.05 consistently on all 3 stages, which wasn't in fact the case, but this is a good approximation that gives us a theoretical solution close to the real, practical values. So we'll take 0.05 for the structural factor. We'll take a relative exhaust velocity of 3.8 on each stage. And I'm going to increase the total delta V required because we're going to the moon. So add another 4 for the transfer orbit to the moon, and then to, actually that's just including another 4 kilometers per second just to reach that transfer orbit. So part A, compute the theoretical optimal mass for each stage and the total mass of the Saturn V. Part B will compare with some actual values that you can look up and confirm on Wikipedia. And what is the percent of the total mass of the Saturn V that was the payload? And let's compare theoretically what it would be and what it was in practice. So I have also on this Excel spreadsheet a section here where the formulas are already entered in for 3-stage rockets. So I think the calculation that I'm doing here is for the 3-stage Acapella rocket in Kerbal Space Program. So for the actual Saturn V, let's put 50 metric tons. Let's go with 0.05 for the structural factor and put this up to 3.8 for the exhaust velocity on all 3 stages. That's not the case, but if you could sort of average and include the higher exhaust velocity in space, that gets us pretty close to the actual values. And for the final delta V that we need to actually not only get into orbit around Earth, but then get on the way to the moon, we will increase this to 14. So here's my theoretical results. 3rd stage, about 146 metric tons. 2nd stage, about 570 metric tons. 1st stage, about 2,200 metric tons, making the whole thing about 2,942 metric tons, 2.9 million kilograms, roughly, for a payload of 50 metric tons, or 50,000 kilograms. Okay, so then looking up actual values for the Saturn V and comparing with these theoretical values that I just computed, I'm getting these values from Wikipedia, which also references NASA websites. I mean, I am choosing relative exhaust velocity and structural factors that give me a good fit to the actual data values, but it's a really good fit with reasonable approximations for those structural factor and relative exhaust velocities, if they're assumed to be the same in all 3 stages. So with a payload of 50 tons in my theoretical model and the actual value, my stage 3 comes out theoretically. In the theoretical model, that stage 3 was about 146 tons, and in actual practice, it was about 120 tons. Stage 2, theoretical value around 570, but in practice, it's about 485. Stage 1, roughly 2,228 tons, theoretically optimal, and the real value was very close to that, giving us a total mass for the rocket that is in theoretical and actual value very close at around 2,900 about 3,000 tons. But very close values, and also significantly, I think here that the theoretical optimal payload to total mass ratio theoretically is very close to what it actually was in practice. I think that was pretty satisfying to see that come out to be so close there. Okay, so I know I've totally hit the limit here of what's long enough, so let's just say that things that we could do continuing on further would be to extend this model to handle different structural factors in each stage and different relative exhaust velocities in each stage. And I do go into that in the Kerbal Math and Physics Lab and the written out version of what I'm presenting here in this video. And there are other additional examples besides just the ones that I'm doing here in this video. But let's just finish off with one last example that we can illustrate in Kerbal Space Program number 8, two-stage rocket that's going to lift 500 kilograms and has the following specifications. Let's take structural factor to be 0.5. So in experimenting in Kerbal, I found that the structural factors are really significantly higher in that simulation than in real life. So we'll take a 0.5 structural factor for each stage, and relative exhaust velocities, let's call it 2,700 meters per second on both stages. And let's take a target velocity of 3,000 meters per second for low Kerbal orbit, which is a sort of delta V budget that includes, gravity losses and drag losses during launch, because actual orbital speed is about 2,200 meters per second, 2,250 meters per second, but to include some additional delta V to get up to altitude, get through the atmosphere, 3,000 is a common budget number that will be sufficient. I mean, less than that wouldn't really be sufficient. So we'll find the theoretical optimal mass required for each stage in this two-stage rocket, and the theoretical total minimum mass required, and then just build a rocket in Kerbal that can reach 100-kilometer altitude and launch a payload of 500 kilometers, and see how that compares to these theoretical values. So I'll go back to the two-stage section here, two-stage rocket, and we are going to set our payload at 500 kilograms. So it doesn't really matter what the units are, but just to make sure it's clear there, I'll put that as kilograms, and I'm going to choose 0.5, and I'm going to choose 2,700 meters per second. So you could put 2.7, or you could put 2,700 meters per second, so that's fine. So if I make this meters per second, okay, so there's the result with 2,700 meters per second for the relative exhaust velocity and 3,000 meters per second for the total delta V required to reach orbit. Stage 2 should be around, well, this is actually kilograms now. Each of these is kilograms because I used kilograms. I'm measuring this value in kilograms. So that makes it about 2.9 tons, metric tons, or 2,889 kilograms for stage 2. Stage 1 should be about 19.6 tons, or 1,959 kilograms. Total mass for the rocket theoretically should be about 23 tons, 22,979 kilograms, according to this calculation here. So let's take a look at a sample rocket built in Kerbal that fits pretty close to these values. This is the rocket that was launched at the very beginning of the video, and recognizing that this will take a while to run through the whole build and all the details, let me just summarize by comparing both the theoretical ideal model with the model that I built here in Kerbal Space Program. One of the first things you have to know to compare these models closely is that in Kerbal Space Program, the stages are numbered in a reverse order than is the common practice in rocket design, and in a reverse order to what had followed all through this video. So, for example, here with this model in KSP, stage 0 is the payload. Stage 1 is the upper stage. Stage 2 is just a decoupler between stages. And stage 3 in this model in KSP is the lower stage. Nevertheless, I think it's really satisfying to see a model built here in KSP that fits very closely with the values expected in an ideal theoretical model. And one thing I've learned here is that the structural factors in the standard game are fairly high compared with real values in real life. So I'll end here, closing out with an evening launch of this rocket, the Lagrange 3.4. Thank you very much for watching, and I hope this has been interesting and educational.